ya, kinematika ini, dan saya minggu ini Selasa dan Kamis rasanya kita sudah akan selesai bab mengenai gerakan partikel, baik nanti rectilinear maupun curvilinear, dan saya ingin mengadakan sedikit kuis. Gitu ya. Nanti saya akan bicarakan dengan Pak Andi Kusoyo dan juga asisten. Kemungkinan kita akan membuat kuis minggu depan. Jadi hari Selasa kita akan bikin kuis atau ujian lah selama 1 jam mengenai bahan bab 12. Di bab 12 mengenai partikel, karena saya ingin mendapatkan suatu input dulu dari Anda, bagaimana dengan pelaksanaan perkuliahan ini, apakah ada masalah nggak, sehingga satu-satunya jalan untuk mengetes adalah melakukan suatu kuis atau ujian. Itu kan enaknya dosen dan tidak enaknya mahasiswa, gitu ya. Jadi kita ingin melakukan itu supaya saya bisa mendapatkan inputan dari Anda bagaimana pelaksanaan itu. Oke ya, jadi saya harapkan sampai Selasa Kamis ini kita akan selesai mengenai gerakan partikel, baik rectilinear maupun curvilinear yang akan saya terangkan. Oke ya, baik, saya mulai aja.
Permisi Pak.
Ya.
Saya Muhammad Zaid Akbar, 1362045. Saya boleh nanya nggak Pak ke Bapak? Jadi ada mahasiswa inter di kami yang masih belum mengerti gitu Pak kosakata dalam bahasa Indonesia di mata kuliah Bapak gitu. Jadi mungkin kalau bisa kalau boleh minta tolong Pak, nanti balengol gitu Pak untuk kuis dan lain-lain.
Okay, very good. Okay, good. So, well, it's better for me to do the English then, right? Because I think most of the Indonesian students in regular class is able to understand my English. Okay, so I think it's better to do it in English, right? Most of it. Then, but I will I will try to do it in Indonesian if there is a question from the regular students. Okay?
Is it will be all right?
Very good.
That will be all right. Thank you, sir.
Very good, very good. Thank you for your input, because otherwise I didn't know about that. Right? Good. Now, last week we discussed on we call it rectilinear motion, which is a motion in a straight line. So if I have motion in a straight line like that, it is actually rectilinear. But of course, the particle generally doesn't, move only in rectilinear. Generally, it will move in curvilinear, right? So it will make a curve, and also other motion which is not only rectilinear, but combination between rectilinear and curvilinear. So we'll discuss on general motion in particle, which is more or less on the curvilinear motion. So it is general curvilinear motion. It means a motion of the particle which has a curvilinear motion, right? So this is one thing. Good. So curvilinear motion occurs when particle moves along a curved path. So it's not a linear, it's not a straight path, but it's a curved path, right? Because it is in 3 dimensions. The path is often described in 3 dimensions. So we will use vector analysis. So you have to understand the vector calculus, and it's not enough for the linear, but because it is moving in the curve, so the position, velocity, acceleration, it is better to use it in vector analysis. So in the kinematics and dynamics, it is important that you understand the vector analysis, right? So the vector, the vector analysis, the dot vector, and also the plus sign. Okay, so you have to look again in the vector analysis in your calculus, right? Good. Right. Okay. Bagas, you want to? Okay. No. All right. So as only is also in rectilinear motion, then we have to analyze the position and displacement. Right. So this is the path, right, which is curve, and this is the frame of reference. We will discuss more on the frame of reference. The frame of reference is actually, this is, thank you, Pandi. Then the quiz and the homework will be given in English, so it will be all right. So the O is actually the frame of reference. The frame of reference either static, which is stay in position, or move, or move in the same velocity. So there will be no acceleration at that point of the O. So if this is the particle, so the position of the particle, we call it the R, right? And this is the S, which is the displacement, right? That's the S. Okay, so remember the R is vector, right? And then, of course, then we will have then the R, the particle move to R accent. So this is the delta R, right? Which is, of course, the straight line. The delta R is straight line, where the delta S is actually, there will be some kind of curve. But if delta R is very small, then delta R will be equal to delta S. But delta R is a vector, and delta S is not a vector, right? So you know that R accent will be R plus delta R in a vector. Okay? So vector analysis is very important in here, right? Good. So that will be the displacement delta R, and we will have to use the vector analysis, or R accent will be equal to R plus delta R in vector. Good. How about the velocity? This is the it's not vector position. It's not vector. V average delta R per delta T, and of course the velocity, that, and this is the V, right? And the V is the tangential of the path. So the V is actually tangent to the path. So yeah, tangent, you know, okay, right? So, and then we will have this is the vector, which is V equal to dr per dt if it is very small. Okay, so once again, V is tangential to the path. Okay, good. And the speed is V ds per dt if it is if ds is is a curve actually, but R is actually a straight line. Okay, so this is the velocity. Once again, velocity is tangential to the path, right? And then we will have acceleration. So what is acceleration? Of course, in the position in here, for example, the velocity is v, which is tangential to that curve, right? And this position become v accent, right? So it is the difference between v accent and v, which is acceleration. Yeah, it is the acceleration. Okay, so we have the average of delta v per delta t. Delta v is actually, the difference between v accent and v, right? And then, of course, then we will have, all right. So this is the path, so v and v. So the average is a delta v and delta v divided by delta v. So because it is the difference between v and v accent, which is actually acceleration. So it is good if we have not the path, the curve is not the path, but the v. So this is not path but v, right? Because of we have the v, then we can calculate the average, the acceleration. Then that is called the Hodograph curve, right? So what is Hodograph curve? The Hodograph curve is, if this we have the O accent, which is this, so this is the v, and this is v accent, right? Because it has different direction, right? The v and v accent difference. If we have, we can calculate, we can make a curve which is v and v accent, which is the same from the same O accent. So we have v and v accent, and the delta v, of course, it is the tangential of the Hodograph curve. Okay, so the Hodograph curve is the v curve, right? It's not the path curve, but it is the v curve. And we can have the delta v, because v accent will be v plus delta v, right? And then we can have, this is the Hodograph curve, has become the A. Right? Of course, A is not tangential, or A is tangential to the Hodograph curve, right? So A is tangential to the Hodograph curve, like V is tangential to the path curve. Okay, so then A dv per dt, and of course A is square r for t square, and A is not tangential to the path. V is tangential to the path, but A is not tangential to the path. So this is we call it the Hodograph curve. Any questions? Okay, I will continue then. Right. In order to analyze curvilinear motion, then we will have three methods. And you remember, it's always in curvilinear motion, we can analyze the motion and three different methods, right? The first one is using the rectangular components or Cartesian coordinates, right? So if I have occasionally the motion of particle can best be described along a path that can be expressed in terms of its x, y, z coordinates. So we're using the Cartesian coordinate, right? Then this is the first method is using the Cartesian coordinate, right? Like that. This is the x. This is the path in curvilinear, and this is the particle, the position of the particle. The position of the particle can be described in Cartesian coordinate, which is x, y, and z, right? And the vector itself is I, j, and k, right? So this is the particle. Oh, sorry, the coordinate system, x, y, z, and the vector in x direction is I, and j, and k. And of course, then the r, this is the position of the particle, can be described as xi plus yj plus zk. So this is the vector in 3 dimensions. Okay, so this is in 3 dimension coordinate system. So we will have r xi plus yj plus zk. Right? So how to describe the position of a particle using the Cartesian coordinate x, y, and z. There will be another 2 coordinate system, which is we will discuss it later on, which is the normal and tangential, and also the polar coordinate. The polar coordinate is the most complicated one, right? But in a simple curvilinear motion, then it might be that the Cartesian coordinate will suffice to analyze that motion. Okay, so if I have r, and of course the magnitude of the r itself will be r net, right? This is using the Pythagoras theorem. So r is that kind of equation. You know that, right? In factor calculus, then it will be. The other one is of course, and the direction of r is specified by the unit vector. So r divided by r, right? So this is the unit vector in the r direction, right? The r direction is specified by. Okay, good. Right. Now, how about the velocity? Yes, of course, the velocity is always tangential. The slope, the tangential or the slope of the curve path, curvilinear path. So v will be also vxi plus vyj plus vxk. Right? And how to do that? V will be equal to dr per dt, right? Which is equal to d per dt xi plus d per dt yj plus d per dt zk. Right? And then we will have, if I have d per dt xi, right, will be equal to I dx per dt plus x dE per dt. Right? This is the simple calculus. D per dt xi will put dx per dt I plus x d per dt. Right? But what is dE per dt? The I is actually a unit vector. Okay, I is unit vector in the x direction, and the unit vector is constant it doesn't move, it doesn't change with time, with t, right? Because it is a unit vector, right? Unit vector in the x direction, it will not change. It is constant to the time. Therefore, di per dt will be equal to 0. Because in differential calculus, if it is constant to the t, then di per dt will be equal to 0. Okay, so this equation will be dx per dt I. What is dx per dt? Dx per dt is actually velocity in x direction. So Vx, right? So then we will have, because it is the velocity in the x direction Vx, then the same, this is Vy, and this is Vx. So then we have V dr per dt will be equal to Vxi plus Vyj plus Vzk. What does it mean? It means that the velocity of the particle can be described into the sum of the velocity the x, y, and z in the vector form, right? Or the v is actually can be described, can be separated into different velocity in the x direction, y direction, and z direction as a vector, right? So this is the v. Now, as I told you before, we will talk a lot on vector. Okay, good. And of course, Vx will be equal to x dot, Vy, y dot, and Vz, z dot. Okay, so that is the velocity, right? So, and the v, of course, the speed itself. Okay, the magnitude of the velocity, sorry. Good. And of course, then we will have acceleration, right? Once again, also A will be equal to AXI plus AYJ plus AZK, which is the same because A dV per dt, and the same will be equal to. Okay, and of course the AX will be Vx dot X double dot. Okay, and A, of course, the direction of A is not tangential or slope to the S, yeah, because the A is tangential or slope on the rhodograph curve, as we mentioned before. Okay, good. Now, then the magnitude of A is like, okay, good. Right, and the curvilinear motion using the Cartesian coordinates is better described in a motion of projectile. You know the motion of projectile in high school or right. So this is the xy, because only two-dimensional. The motion of the motion of particle in gravitational methods like that is two-dimensional. So we have the x and y. So this is the position x null and y null, and this is the velocity v null, which can describe by v null x plus v null y. Right, and then we have a gravitational acceleration, which is constant, 9.81 meter per second square, or 32.2 feet per second square, which is constant. So we will deal with a constant A, right? And then we will have horizontal motion, because the horizontal motion, AX will be equal to 0. There will be no, acceleration in that direction, right? So AX will be equal to 0, but AY will be minus G, right? AX will be equal to, and so the constant acceleration V will be V0 per AT, A equal to 0, so Vx will be V0 x. So the velocity in horizontal motion in x direction will be equal, will be the same, right? And then we have the x, and also Vx will be equal, right? But of course, then we have the vertical motion, which is AY will be equal to minus G. Then we will have that kind of equation, right? And then by doing so, then we can calculate the position in it. Okay, so this is yeah, this is the projectile motion. Okay, right, good. Any questions on the Cartesian method? So all the position, velocity, and acceleration is described into X, Y, and Z component, which is I, J, and K component, using any questions? Right, good. Now the second method is using normal and tangential components. So the motion of curvilinear the curvilinear motion of a particle is described in normal and tangential components. Okay, what is normal and tangential component? When the path along with a particle is known, if I know the path, then it is easier to describe in N and T coordinates, which is as normal and tangent to the path, right? And have their origin located in the particle. So this is the motion that we know, right? Because I know the path. The path will be travel in that direction. So I can, sorry. So I can make in the normal. Oh, sorry, I didn't, I didn't have the pointers. Sorry for that. Right. This is the normal path, normal direction. Sorry, and this is the tangential. Okay, so we will know the particle and the motion of particle using coordinate system which is normal to that and tangential to that. Okay, good. Right, just like that. If I have the position, the path, right? So I can describe this is the N, which is normal to the path, and moving S, for example. This is a N, which is normal to the path, N, which is T, which is tangential to the path. So the component is, there will be UN and UT, right? So this is the unit vector in the normal, and you may imagine that O itself, it will be not fixed. it will be moved according to that, right? And this is this position. I will describe it later. Okay, so right. So how to do the position of O accent? It will depend on the path, right? For example, if I have a very small TS here, and I make a normal to that point, and normal to that point, it will meet to the O accent, right? And this is the rho. Rho is actually, this is the rho. Rho is actually the radius of it. And if it is the curvature is very steep, then the O will be smaller compared to that, and the radius is small. But if it is change the direction, then it may travel from here to that, right? So how to find the O accent is actually you do the curve path, make a normal, and the other is making normal, and then this is the O accent, right? This is we call it the radius of curvature. Rho is the radius of curvature. Okay. Why it's important? Well, it's important that it is of curvature, so we can have it, right? Good. So how about the velocity? The velocity, if I have co-accent, which is the radius of curvature, v is of course then a tangential or slope of the curve. So the v will be equal to v ut, right? V is the magnitude of the velocity. Ut is actually the direction, tangential, because V is always tangential to the curve path, right? V is always tangential to the V path. Therefore, it is in the direction of Ut. Okay. Right, so V is equal to S accent. Okay, of course, then if it is the curve is changing, then the direction of V is also changing. It's like in the Cartesian coordinate also. Right. Good. Now, to better understand this result, consider the following two a special case of motion. If the particle moves along a straight line, then radius will be to will be to infinity. So, for example, if this is the straight line, if the motion is straight line, just like that. Oh, sorry, straight line. So if we have the normal, will be that, and normal will be that. Okay, so of course, then in that case, the radius will be equal to infinity. Why? Because it will not meet. It never meet, right? These two lines, the normal line, will never meet, right? If it is if this is the particle, this is the particle moving like that, right? So it will never meet. In this case, then of course the acceleration in that direction, normal direction, will be equal to 0, right? Because this is in the normal. In that direction, it will be in the t direction, right? Because it is tangential direction. the tangential direction, then of course the acceleration will be the difference between the speed there and there. V accent, and there is V, delta V per delta T, so it becomes the AT. So this is just like in rectilinear, if you still remember, the rectilinear motion. So the AT is there, right? But the AN will be equal to 0. Okay, so this is a special case, right? The other case is actually if I have, if the particle moves along a curve with a constant speed, right? Along a curve, for example, if I have cylindrical motion like that, right? If I have, if I have, I will have difficulty in. If I have a particle moving that in the same speed, if I have constant speed, right? Of course, then I have the same R, which is constant. Okay, if there is a constant, then we will have what is called, because it's a constant speed in tangential one, so AT will be equal to 0. But the normal will be equal to V squared over rho, which is called centripetal, right? Because then I will have, this is AN, this is AN. Oh, sorry, this is AN. Yeah, the normal acceleration, which is equal to V squared divided by rho. So this is what was called centripetal motion, centripetal acceleration, and this is what the planet, or if you have the motorcycle having, moving in the cylindrical like that, so they always get the centripetal acceleration. Okay, that's why it can have the same position. For example, if you know the motion of the motorcycle in that kind of. So this is the two special one, right? If it is straight line, then the radius will be equal to infinity. Then it will be 0. Then we will have AT. But if it is the constant speed like that, then it will be special Blackwell. Okay, good. Now, so then the general motion is, for example, this increasing speed, right? And then change of direction, because this is the AN, AT, and A like that. And then, AN, AT, and this is the acceleration A. And then we will changing direction, because then we will have AN in direction, AT in direction, and A in direction. And if it is the straight line, then become we call it rectilinear motion, where A will be. So this is the general analysis of curvilinear using the normal and tangential component, which is moving and then changing direction accordingly. Okay, good. Now, this is the cylindrical okay, good. Any questions before the last component.
Izin bertanya, Pak.
Ya.
Kan tadi dijelasin kalau di analisa pakai komponen tangensial dan normal ini kan katanya di slide Bapak yang saya baca itu originnya itu selalu berada pada pusat benda ya, Pak?
Oh ya. Oh.
Nah, lalu
ya,
untuk
artinya
bisa
origin.
Ya, silakan, Pak.
Ya, jadi di situ karena titik frame-nya, frame apa namanya? Yang kalau Anda bilang kalau dibandingkan dengan apa namanya? Cartesian, di mana frame of reference-nya itu apa namanya? Constant, di situ kan tidak ada frame of reference-nya. Tidak ada frame reference yang constant kan? Karena aksennya kan bisa berubah-ubah kemana-mana. Jadi kita anggap dia titiknya di situ, titik pusat di situ, dan kita analisis pada benda tersebut. Itu aja sih.
Jadi sebenarnya sistem komponen tangensial dan normal ini bendanya juga sebenarnya masih punya reference point ya, Pak?
Reference point di benda tersebut.
Oh, berarti kalau reference point di benda tersebut, pertanyaan saya maksudnya gimana kita bisa nyari kecepatannya ya, Pak, sampai ke percepatan? Karena kan gerak bendanya
memang
nggak
kita juga bisa mengatakan frame titik frame-nya berubah-ubah aja lah gitu ya, supaya mudah aja lah. Dibanding kalau Cartesian yang titik frame of reference-nya apa namanya frame reference-nya constant, pada komponen yang normal dan tangensial titik frames-nya berubah-ubah. Jadi kecepatannya kecepatan pada dirinya sendiri terhadap kecepatan sebelumnya.
Sistem ini berarti hanya menjelaskan tentang percepatan dan kecepatan benda ya, Pak? Karena sudah dijelaskan kalau masalah gerak benda ya. Terima kasih, Pak.
Ya, oke. Terima kasih sekali. Bagus pertanyaannya. Yang lain? Dan apa namanya, normal dan tangensial itu nanti banyak dipakai karena nanti kalau kita bicara mengenai kinetik juga banyak dipakai itu. Dan itu bisa berubah-ubah memang. Oke. Nah, yang agak complicated adalah cylindrical components, karena itu jarang sekali kita menggunakan cylindrical component. Karena kemudian apa namanya, mathematically juga sangat complicated. Cylindrical component, rasanya di ujian juga jarang kita pakai yang cylindrical component. Yang banyak dipakai Cartesian maupun yang apa namanya, yang normal tangential. Nah, the cylindrical component is more complicated than Cartesian or the normal tangential because cylindrical component mathematically is very complicated. Right? It's because we will use the polar coordinate system, which is complicated for this one. But I will try to do that. So right now in the polar coordinates, then we will have the fixed frame of reference, which is 0, and this is the path. Right? If I have the path, then this is the coordinate that we decide, right? And if I have the particle in here, so the particle is described into two components, which is what is it? This is theta, yeah, and r. So this is the what is it? The angle between the component in x or in the x. This is the theta, and this is the r. So the component is actually r in r direction, and u theta, which is perpendicular to the r. Right. So if you have the fixed fix a point like that, and you, for example, you see the aircraft, so the aircraft moving in curvilinear can describe into theta and r, right? Not x, y, z, but theta and r, right? Because this is also a good representation of the position. Okay, but because of the theta and r, the mathematical is a little bit complicated. So the position is r, which is r delta r, right? And right, so this is the position, and we have the theta, and of course, then the v, which is r accent, will be r accent or because there's some kind of theta, and then we know that OR is theta accent, U theta, and etc. And then the V is like that. It's complicated. I will never use it. Then we will have that kind, which is VR is R accent, but V theta is R times theta accent. Okay, which is V just like that. Okay? And the acceleration is also more complicated because it has some polar coordinate on that double accent. So spatial coordinate, which is more complicated on that. So I will not use that. If you want to learn more about that, you can read in Hibbeler, but I will not use it, right, for the exam or other things, because it use because then I have to have theta as function of t, etc. Will be more complicated in three-dimensional. Okay, right. That is the particle. Right? Moving on the particle. Any questions? So we will have last week we discussed on rectilinear motion. In here we will discuss on curvilinear motion, which is general curvilinear motion. The general curvilinear motion can be can be analyzed using first Cartesian coordinates, which is very easy, and the second is the normal and tangent analysis, which is also relatively easy, but we can also cylindrical component, polar coordinate system, which is more complicated mathematically. So I think it's better to use Cartesian or normal and tangential. Any questions? No questions? So everything, Fernando, please.
Selamat pagi, Pak. Perkenalkan, nama saya Fernando Di Pratama, NIM 029. Saya ingin usul aja sih, Pak. Kayak tadi kan di awal diminta bahasa Inggris gitu kan, Pak. Cuma saya tuh masih kayak kurang paham jika full bahasa Inggris gitu, Pak. Jika memang memungkinkan, kalau misalnya ada tambahan bahasa Indonesia di belakang-belakangnya gitu gimana, Pak? Untuk penjelasan yang lebih yang lebih kompleks gitu untuk bahasa Indonesia, karena ya
sorry
kurang paham seperti itu sih, Pak.
Terima kasih, Pak. Baik, saya akan perhatikan. Jadi saya akan bilingual aja ya, bahasa Inggris kemudian saya pakai bahasa Indonesia gitu ya.
Iya, Pak, itu usul dari saya sih, Pak. Jika Bapak tidak keberatan dan teman-teman mungkin bisa memahami seperti itu, Pak. Terima kasih.
Bagus, nggak apa-apa. Jadi saya campur aduknya. Terima kasih. Pak Andi, mau bicara?
Betul Pak, jadi mungkin untuk pengajarannya mungkin perlu bilingual. Saya biasanya bilingual, jadi pertama penjelasan bahasa Inggris misalnya satu slide bahasa Inggris terus dijelaskan ulang dengan bahasa Indonesia per slide, bisa begitu mungkin Pak. Saya biasanya
ya, sorry. Jadi ini bagusnya apa namanya kuliah seperti ini, jadi saya mendapatkan suatu input. Tapi Fernando tadi, Anda yang tadi masih jelas bisa nangkap nggak?
Untuk yang tadi Pak mungkin masih cukup jelas sih Pak, karena ya banyak rumus-rumusnya gitu. Mungkin nanti bisa ditambah dari pelajaran di luar kuliah gitu Pak. Terima kasih.
Very good. Oke, nanti saya terangkan bilingual aja ya, bahasa Inggris, kemudian saya terangkan juga dalam bahasa. Bagus, good. Ada lagi masukan yang penting. Enggak ya? Baik, kalau enggak, Anda absen, saya tidak tahu absennya Pak Andi, absennya di CX cukup atau harus pakai EduNext, saya tuh nggak ngerti mengenai.
Begini Pak, untuk daftar hadir lebih baik di akademik saja, di CX gitu, silahkan diisi di situ. Tapi walaupun misalnya nanti biasanya sekarang tuh sistemnya kalau misalnya mahasiswa buka EduNext, itu nanti akan terekam otomatis di CX. Nah, begitu. Nah, tapi untuk amannya masuk saja ke CX supaya memang dipastikan bahwa sudah terrecord gitu. Kalau ternyata pada saat hari itu misal sempat buka-buka EduNext untuk kinematika dan dinamika, biasanya sudah terrecord di CX. Tapi lebih baik pastikan saja di CX gitu. Jadi utamanya mungkin dicek di CX bukan di EduNext gitu.
Baik, terima kasih. Jadi tolong CX gitu ya. Teman-teman gitu semuanya ya, mahasiswanya ya.
So please check your attendance list in academics.
Yeah, in CX. Yeah. Please, any other comment? Very good. This Thursday I will continue on the article. Jadi hari Kamis besok saya akan melanjutkan mengenai partikel, dan hari Selasa minggu depan saya berencana mengadakan kuis atau ujian. Ya, jangan takut lah. Ini saya hanya ingin memberikan satu masukan, apakah bisa terima atau tidak, sehingga kita bisa memperbaiki kuliah ini dengan baik. Dan percayalah, we don't like to fail you. Kami tidak suka Anda gagal. We don't like to fail you. Itu.
Permisi Pak.
Yes.
Mohon maaf penjela Pak, apakah emang nanti akan ada PR atau sesuatunya gitu Pak?
PR?
Iya Pak,
yeah.
apakah nanti akan Oke Pak, terima kasih Pak.
Jadi tentu saja nanti ada PR atau ujian atau segala macam. Nanti kita diskusikan dengan Pak Andi dan juga dengan asisten, apakah tentunya PR. Pak Andi, silakan Pak Andi.
Gini Pak, untuk assessment, jadi mungkin ada kuis mungkin pasti ada. Terkait PR itu nanti disesuaikan, bisa jadi mungkin pada saat partikel ini tidak ada PR, tapi nanti pada saat yang rigid body ada PR gitu. Tapi ya itu akan disesuaikan, tapi PR dan kuis ada. Kemudian nanti untuk ujian pasti akan ada ujian yang mengujikan tentang partikel dan rigid body gitu.
Ya, oke. Jadi PR pasti ada, terutama yang rigid body, karena rigid body lebih complicated. Yang partikel nanti kita lihat apakah kita pakai PR atau juga dengan kuis.
Atau cukup dengan kuis, betul Pak. Jadi kalau misalnya dilihat cukup dengan kuis, berarti bisa jadi PR mungkin skip. Tapi kalau misalnya ini ya bisa jadi yang lain.
Ya. Gitu ya. Baik, terima kasih. Kalau begitu, terima kasih atas perhatiannya, dan saya stop recording.